Hello Kickstarter, I'm Jonathan Torkelson. Thanks for taking the time to check out our campaign. In this video, I'm going to be showing how the QuickDAQ.mikroBUS can be used with virtual microcontrollers in the Virtuoso low-code environment to quickly develop embedded software. So let's get started. We'll start by creating a new Virtuoso project, so let's run Virtuoso. Now let's click on the New Project tab, and you can see a C# Visual Studio 2019 host plugin. This means that we're going to be building a C# desktop application in Virtuoso. So I just need to click and create a new folder. And click Create Project. So this is the Virtuoso low-code environment with the schematic editor. This is where we design an application at a high level of abstraction. So we can just drag an LED component into our schematic from our toolbox. And I'll also drag and drop a momentary push button. And the LED has a is-on Boolean input, and the push button has an is-clicked Boolean output. So what I want to do is just wire them together so that when the push button is pushed, the LED turns on. So I can save the host and push update to Visual Studio 2019. And this pushes this high-level design to the actual third-generation language programming environment. So we can open that up by clicking the Open Visual Studio 2019 button. So this is the application that we just built from scratch, and this is a fully formed C# desktop application in Visual Studio 2019. So we can open up the main window and see our two components that we just dragged and dropped. There's the push button and the LED. So we can just move them around and run the project. So we can push the button, we can see the LED turns on. So what we want to do now is incorporate hardware in the loop, real hardware into this design. And that's what the QuickDAQ.mikroBUS lets us do. So I'm going to drag and drop a microbus board node onto the schematic. And this node represents the actual physical board. It's connected to the computer. So when I click on the node, and you can see it's already found that it's on COM4. So the microbus board has these 8 LED inputs and 4 push button outputs, and then the 3 microbus slots. But what we're going to do first is just wire up the is-clicked momentary push button to some of the LEDs to see the LEDs turn on. So just like that, we dragged and dropped a component, wired some wires up, and now we can run this application again. And when I click on the button, you can see the LEDs turn on. So that's how easy it is to interface to real hardware using the QuickDAQ.mikroBUS in Virtuoso. So what we want to do with this is be able to build and develop embedded software and test it in this environment with unlimited virtual components and using unlimited clipboards as well, so that we can quickly build out what we need to test. So what I'm going to do is create a new virtual microcontroller by dragging and dropping this Visual Studio 2019 empty target node. So I just need to name my target. And I can save and push those changes. So now I reload those changes. And you can see there's now a C project added to the solution. So this, by dragging and dropping that node, that created this entire C project and added it to the solution. So that C project is going to be running on the computer in parallel with the C# project. So both will be running side by side. And this is where I can develop all my embedded software. So what we're going to do is we're going to create a driver interface. And we want to read an analog input, and we want to be able to drive an LED output. So I'm going to create a read analog input function and a set LED state function. So this is I can call this to set an LED state. I can call this to read an analog input. So that's my hardware abstraction layer. And for a actual embedded project, I would be implementing this maybe in a driver that interfaces to real hardware registers. But in a virtual environment, we don't have hardware registers, so we need to do something different. So I'm going to put our actual implementation of these drivers in a sim_hardware.c driver file. So there's our functions in a sim_hardware driver file. The application is going to be calling these functions, and in our virtual environment, it's going to be actually calling these. In the physical hardware project, it's going to be calling the function that interacts with the registers. So to actually do something useful, I need to create some variables. So this variable is going to just store my analog input value. And this is going to store the LED state. So you can think of them as virtual hardware registers. So my read analog input, I just need to return the sim analog input state, analog input variable, and the set LED state, I just need to set this variable to the new value. So all we're doing is reading and writing to these two global variables in memory, in the computer. So for the application, what we want to do is just keep reading this analog input, and if the analog input ever goes above 1,000, we want to turn the LED on, and if it is below 1,000, we want to turn it off. So that's the simple application that we want to develop and test. So I'm going to save that and build the project. So this project will now be running in the background, but it's not going to be actually interfacing with anything in the environment. So what we need to do is be able to expose this to the environment. So I'm going to click on the target and open up the target model builder. So the target model builder is how you quickly and easily build out the interface between the application in the virtual drivers and the rest of the low-code environment. So we can create variables, interrupts, we can create serial streams, events, and a lot more. And right now we're just going to be creating some variable bindings. So I'm going to create a new variable, and we can just start typing analog, and this is going to filter all of the global variables in the application, no matter how big it is. You can just start typing and quickly find your variable. So that's an input. It's coming from C# to C, and it's a floating point. And we're going to create the digital, we call that LED output. That's an output, and it's a Boolean output. So just by doing that, we now have our input port and our LED output. So what we want is for this embedded C program to be interfacing to the real world. We could use other virtual components as well, and just be using any number of components, either from the library or from the community in Montage. So to use the QuickDAQ.mikroBUS hardware, I'm going to be using a RGB driver clipboard and a proximity sensor clipboard. So you can see I've got the RGB driver is on the microbus slot number 1, and the proximity sensor is on slot number 3. So I'm going to wire slot 1 up to the RGB driver, and slot 3 goes to the proximity sensor. So the proximity sensor is going to be my analog input, and I want to let's drive the red LED on the RGB clipboard. So this is an actual PWM clipboard. So these are values from 0 to 1 on red, green, and blue. So Virtuoso is going to create, it knows what code to emit to convert to a floating point. It's just going to be converting it false and true to 0.0 and 1.0. So again, this node represents the clipboard, the RGB driver clipboard at a high level. It's actually doing all of the communication with the clipboard and keeping it in sync so that whatever value is being driven on these ports is actually transmitted to the clipboard very quickly and a low latency. And the same for the proximity. This node is continually reading the proximity sensor and updating this value to whatever is connected to it. So we can just save this, push our changes, reload, and run our project. Okay, so our project is running now. So I should be able to just touch my finger close to this and you can see the LED turns on. And when I move it away, it turns off. So this is the embedded code that's reading the proximity sensor value and turning the physical LED on from the microcontroller code. So this is how we can quickly and easily develop embedded software in a virtual environment. And once we've validated it, we can then go and build our custom circuit boards, but not have to go through that expense until we've validated that the design works. We can use clickboards that incorporate GPS or wireless and all of those individual components that are needed for the validation stage without having to, again, do any of the extra work of actually building out the custom hardware. As this video shows, the QuickDAQ.mikroBUS lets you use any of the hundreds of clickboards or other hardware-in-the-loop components with your embedded virtual device to quickly and easily develop embedded software. I hope you found this video interesting. Thanks for watching, and thanks for your support.